Thanks a lot. Thanks for the invitation. So this is a talk about something which is rather not that new a topic for me, but let's say the last few years. And I fell into this coming from spin glasses, of course. But there will be, you will have to look carefully to see the spin glasses hidden there. So this is based on on this paper, which is with Reza Gheissari from Aukosh Jagannath, two former students at Courant, who are now professors, one in Canada and the other at Northwestern. And this is published in NeurIPS last month, in December. And you have a longer version, which you have access to. And of course, it's a little, I'm bragging a little by saying it's an outstanding award, but that's because I'm really proud. These are, I don't know if you know about, anybody here knows about NeurIPS. So that's really the top conference for this machine learning type things. But the more important thing, so you have 10,000 submission and whatever, 10 outstanding paper award. The important thing is that it's given by anonymously. Papers are accepted by essentially by young people, in my scale at least, young, and who don't know who's, and then so getting a prize from people doing machine learning, much younger, that's the kind of that's why I'm bragging. It's not given by the usual colleagues. All right, so of course, in the title you had SGD. If you don't know what that is, it's stochastic gradient descent. So let me explain what that is. So let's take it from the start. And if you are interested in the spin glasses, this will come later. So stochastic gradient descent and estimation. So let me say what it is. So you have your variable are in RD. So this is the hardest part of the talk, is to remember there will be three numbers, D, P, and M, and to remember what they mean. And the terrible thing is that in this literature, these notations always change. There should be a standard saying, but here, so D is this dimension of the variables, as we will see. And P is an unknown probability, statistics, probability that you don't know. And then you have a loss function, L, which is defined on V cross U. V is the space of parameter. It's inside, it's RP, it's P dimensional, right? So it's parametric estimation, right? You want to optimize a parameter that will give you, I could have said that this P depends on X if you want. Anyway, so, and this loss function, where does it come from? We'll see, but that's the statistical procedure. That's whatever you try to define this loss function. That's a different type of art. This is the, when you do this type of thing, you have three layers. One is information theory, which is can you with the data you have, can you find the P? The second is how to find it, the statistical procedure. That's how you find this L. And the third is optimize, find the minimum of your loss, and that's optimization. That's what we're going to talk about. So the goal here is to find the minimum of, let's say, the population loss is the expectation of this thing. The expectation is in Y, X is a parameter, right? I call it phi. All right. Remember that we don't know the distribution, so in fact, we don't know the function we want to minimize. Okay. So why should we do that
again? What is X there?
So it's a parameter, usually called theta if you do statistics.
It's a bit confusing, but it takes spins kind of a three-dimensional space in our sense, and spins have n components.
It's true.
And J and everything are parameters, beta. Yeah. So say it's parameter space.
But for the moment, I'm not doing statistics. Okay. Let's imagine you want to estimate the mean of a Gaussian. X is the mean.
Back to your slide.
Okay. Wait a second and you'll see. Okay.
But yeah.
So that's just in this slide. Why should we do this, and how do we choose the loss?
We don't know what E is, right? We don't know what the expectation is yet.
We don't know that. So the natural obvious example for statistician, it's, let's say, maximum likelihood estimation, right? So wait a minute. So what is that? Right, you have your distribution depending on a parameter, X here. And what you do in maximum likelihood, let's say you have a fixed distribution. You look at the density with respect to this fixed distribution, called f of x dot, right? And then you want to maximize this, right? And so typically you take the log of the likelihood, and then you try to maximize this. Okay, another one, machine learning, learning a neural net. So I don't know, does everybody know what a neural net is here? So let me explain in a second what kind of thing we're talking about here. The idea of neural net is simple. It's to define a class of functions to do approximation theory. And then, so here is how it works. Here I'm drawing a neural net. So information flows this way. The neural net has 4 layers. At each node here, in order to define your neural net, so here you have a graph, which let's say could be, okay. So on each one of those, and same thing here and here, on each one of those links, you have a weight, let's say W. Okay, so this W1 here is this big matrix here, right? If you have a 4, this is a 4 by 5 matrix, okay? And then you would have another matrix here, another matrix here. And the way the function here is just defined by taking this linear, it would be taken, so you have your input, let's call it X, then you apply W1 to it, then you apply a function. So what is it? Sigma we call an activation function. So what does it mean to apply a function to a vector? You apply it coordinate-wise, right? So if this function is
Point-wise, yeah.
point by point, okay? And then this gives you some, so you apply it at every one of those nodes, you apply sigma, okay? And then you do again the same thing. So you have W2. And then again, you apply sigma here. And then again, you have W3. This defines the, and then you have the last, let's say the last layer brings you to, say P here, or you could call it W4. And this defines the output, right? So now this, if you want, is a function, this Y is a function of X, which depends, oh, I'm sorry, I should not call it X. Let me call the entry Z. Okay. And now what are the parameters here? It's just the matrices W1, W2, W3, right? And this is a function which is parameterized by these guys. This is the simplest of all. So this defines a class of function. Typical functions sigma here are what people in machine learning call Waterloo. Waterloo is just X plus. Okay. It could be the cross entropy. I mean, we will give also, it could be, I'm sorry. You can have all sorts of logistic functions, all sorts of functions of that type, but this defines a class of function. What is remarkable is that, you know, think of it like trying to approximate every function by a Fourier series, right? This goes back much longer. So, and then, so here the story, that this would be approximation theory. There is a universal approximation theorem telling you that you can approximate essentially any function by such things. The difficulty, of course, is to find the best approximation. Right? When you do Fourier series, not difficult. You know the coefficient of the optimal thing, the Fourier coefficient, you know the projection in L2. Here, how do you do that? So how you do that, you have one more function, S, a loss function. And typically you have your true function, let me call it F of Z, right? That's your true function, the one you want to estimate. And your function that you get here, theta is my collection of W, the one defined by the network. And this will be your loss when you average. So typically, of course, as we will see, you don't have access to so what you have are data, right? You have entry and input and output, which are generated by a random thing that you don't know. And so you want to minimize this. So I'll give you examples in a moment. So that's, of course, a very general class. This is the one that is motivating this.
So there's a lot of degeneracy in this in choice of W. Many W's might give rise to the same function, right?
And you will see this is called overparameterization. Interestingly, so the dimension of the parameter in those things is enormous, 10 to the 12. And people are saying, overparameterization is good, right? So we'll see an example of that. Here's another. So if this is too far from what you like, and this is for people like, here's another function just for mathematicians. Right? You take here my loss here. You fix. I'm on the sphere, let's say, in high dimension, and there I took the n like we do in spin glasses, and I have this function here, which is a random homogeneous polynomial of degree p. Right. So the y here, the randomness comes here. It doesn't look like the same problem, but of course, this is a Gaussian. So let's say centered Gaussian fixed mean, fixed variant. And then you add this thing, which is not random. Lambda is a signal to noise ratio. X1 is one coordinate, right? This seems like a crazy thing to do. You have a random polynomial here, and then you add a very simple polynomial, a rank one polynomial. Try to minimize this. Okay, so before we go there, this is a super hard problem. But before we go there, let's remember what I'm describing here is if put lambda equals 0. This is just a spin glass. Right? This is the spherical spin glass. Okay, the P spin glass.
P spin glass, yeah.
Right? So here, if you have lambda equals 0, finding the minimum of such a function, is very complicated. The landscape of this is understood. The number of critical points is exponentially large. Finding the minimum is complicated. If you look at any kind of dynamics to find this minimum, typically it's proven to be exponentially long in n. Right? Now, this is a different problem. What is this problem? If I add x1, so you have your sphere, and let's say x1, one axis is vertical here. So you have the north pole of your sphere. And the question here is, okay, I add this. Why would I do that? If you take k equal 1, this would simply be a spin glass with a magnetic field. And lambda would measure the strength of the magnetic field in the direction x, right? So you understand that when lambda is large enough, then the problem of optimization would be simpler. In fact, if you take k equal p, we will see that this is a problem of tensor PCA. This is a maximum likelihood problem. This comes from a maximum likelihood too, right? This is the link between the statistics thing and the spin glasses, right? But if you look at it, this is a very complicated random function. This is a very simple one, okay? When lambda is large enough, dynamics should find the North Pole, right? In shorter time, right? Okay.
And so how can, I just want to make sure I'm not misunderstanding. How can just waiting on this one coordinate make a big difference to the complexity of the overall picture?
That's exactly the point. So
even if you fix the one coordinate,
the equator, the rest here is in dimension n or n minus 1. So it's, if you take a point at random, it will be at the equator of this thing. Right? You will never find this. But here, this gives you a term in the vertical direction that may win. Right? Brings your dynamics there if lambda is large enough. Okay, well, and this is understood completely. Okay? So for instance, when lambda, if k is 1, right, then you have a magnetic field which will bring you pretty quickly up. Okay, and we will align with this. Right? If you look at the Gibbs measure, you can prove that it will be in at a positive latitude. Okay, this can be proved. When k is larger, things are much more interesting. Okay, and in particular, the statistics problem, I'll come back to that, is interesting and complicated.
I see. Suppose you're really far away.
I mean, as soon as you can, I mean, escaping the equator is very difficult because the hemisphere in high dimension is of exponentially small probability, but you have something pushing you there. Right? So that's, you have a battle between entropy and drift.
But I mean, if you just condition on x1 being equal to 1,
yeah,
does that really change the fundamental complexity of the problem?
Completely. Here you don't, of course, you start from the idea that you don't know in which direction is x1. Right? When you I could have written here x inner product with a vector e, and e is unknown. Here I choose e.
But like in random case that if I fix one literal, that doesn't change the. I don't know. Maybe I should just let you go on. But.
Okay, so here it changes a lot. All right, so how do you do that? typically, of course, you don't know the distribution, but let's say you have data. So you have M, now that's the third thing. You have M data points of the distribution P. Okay? And so one natural idea, of course, is instead of looking at this the true loss, you look at the empirical loss and try to optimize this one. Now this is a random function, random because you have the data here of the parameter X, and you want to optimize it. So of course,
So X is in your RP or whatever it was.
yeah, that's the parameter.
Parameters.
In the example of the neural network Z, what you have
That's the
Y
M's.
would be little z, right?
No, X is theta here. X is the collection of W.
That's all. I understand X, but what you had is randomness, little y, that would be the input to Z.
Yes, that's both in the neural net, it would be the input and output. Let's say you do supervised learning.
Input and output.
Okay.
As it there.
All right, so where am I here? So what I was saying here about the empirical loss, this is very natural and done, of course, in the classical regime when the dimension D and P are fixed, and the data tends to infinity, right? At least in a regime where M is large enough as a function of D and P. I will not go there. But then, what you do is just gradient descent, practically, you do gradient descent for this empirical loss. Okay, maybe with some random point initialization. And this classical regime, the empirical loss might be close enough to the population loss for this gradient descent to find the minimum of phi. Right? This is a very long story. I won't go there. Because in fact, I'm not interested. Of course, you could also, and this is also done, try instead of taking a gradient loss, you could take a gradient flow. You could take a Langevin dynamics by adding some extra noise if you want to avoid traps. Okay, that's a long story, but that's not the one I want to tell. So, and of course, you could also try stochastic gradient descent. So that's really the go-to method for large-scale optimization problem. So what is stochastic gradient descent? It comes in a million variants. You could take mini batches, different learning rates, reuses, acceleration, momentum, all sorts of things. It's an industry that I've just discovered, which is in fact pretty delicate and interesting. But I won't, of course, in order to give a talk, I just choose here the simplest case. So this is called the online SGD, and here it is. Right, so you have your position X. This is, remember, the parameter. At the next step, you take the former step, and then you subtract. Delta is called the learning rate, the gradient of your X at the position before, and at this new YL. Right, so each new data, you do that. Taking a mini batch would consist in, when I say mini batches here, consists in taking the sum of these guys over a few of your data.
With the same X.
Right, with the same X. And then you have a random initialization where you have to start. Okay, so that's a very, very simple algorithm. So why would you do that rather than the empirical?
So you're not sampling everything, you're sampling some subset, or one of these mini batches you're talking about?
So for here, the mini batch is size 1. I just have one guy. So that's called online. You have one new data point, you put it there, you make a step. Another data point, you make a new step, right? That's the simplest version. That's the shortest. If instead of taking a mini batch of the minimal size online, you took the full batch, then you would have the empirical, the gradient of the empirical thing, right? So, and then you can choose mini batches in between. So for the moment, I'm taking the most SGD possible, as far as possible from the classical GD, gradient descent. Okay, so why would that be interesting? Why would that be better? Of course, it's better first for practical reasons. In situations where you have a lot of data, very big things, just computing the gradient on your whole data set at every step is enormously slowing down your algorithm. This is much faster. You just take one after one. Would that work? So at least it seems more doable, but understanding its performance is complicated. Okay, so now our interest is in understanding this evolution here in the regime where both P and D, the dimension of the parameter, and D, the dimension of the data space, tend to infinity, but when M, the size of the sample is not too large. You don't have, remember, this thing will be gigantic. This could be 10 to the 14, 10 to the 10, 10 to the 12. So for M to be much larger than that, this would ask for an enormous amount of data, right? And which usually does not exist, right? When you say big data, in fact, people don't realize that.
Sorry, so I lost track of your notation. The M is what again?
the amount of data, the number, look at that. This is why I said here. What I have the size of the sample. Okay, I have Y1 to YN. Okay. All right. So in fact, in most problems, in big data, the dimension is large, but the amount of data we have is not large enough to just be in the usual regime of the law of large number and this type of thing. Okay. Nevertheless, if you talk to people doing this, this is what is really being done. I jumped into this because of precisely we're talking about the Center for Data Science, because we're chatting with Yann Lecan a long time ago, and people doing this seriously would tell you they're adamant. Nobody would ever try gradient descent with the empirical laws. They would do stochastic gradient descent, and it has all sorts of magical properties. Right? I understand. Okay, so a very short history of stochastic gradient descent, which I discovered recently. It was introduced in '51 by Robertson Monroe. And as I said, in the classical finite dimensional setting, P and D, let's say, are fixed, and M is large enough, that you have enough data, then the asymptotic is very well understood. And so at the core of this line of work, you have the idea that when the step size tends to 0, the delta, the trajectory as SGD, appropriately rescaled, converges to the gradient flow of the population loss, okay, which seems reasonable. That's the law of large number type thing. And then, so you have this kind of pathwise limit theorems. You have functional central limit theorems. So you have Gaussian fluctuations around that, diffusion approximation, and even large deviation principle in this simple context. All that is well known. If you want a mathematical review of this, look at this course by Michel Benaim in '99, and so which was readable by mathematicians. By that I mean people not specialized in optimization. All right. So in the recent years, the interest has shifted to high dimensional setting, where you're constrained by the amount of data or the runtime of the algorithm. You remember the runtime of the algorithm is exactly the size of your data because you use one data once, right, at each step. So in this regime, you cannot simply take the learning rate to be arbitrarily small, because otherwise this would force a really very large sample size. So what is going on there is not clear. So this is a common issue in high dimensional statistics. And for instance, you could go to this recent survey, which is interesting. Okay. So there is now progress in some of these limits. I'm giving a few references here. My colleague, Eric van den Eyden and Rotzkopf in Courant, Montanari in Stanford, with May and Guyet, Shiza in Paris, and back. And so these are interesting things where the dimension of the parameter space diverges, but the dimension of the data remains constant. It's called the mean field regime. For SGD with constant learning rate, there is also recent progress, for instance, by Léon Boutou, who works with Yann Lecan, in fact, at Facebook now, Nilo Srebo and Ward, and many more. And also from some non-convex situation in his papers, and these are my co-authors. All right, so that's a brief history. And there's also a line of work coming from Florent Jacala and Lenkas Deborova at École Normale, and now at EPFL, I'm sorry, and their collaborators on these things. And finally, all that can be inspired by, there is, of course, a physics perspective, which is called DMFT, dynamical mean field theory, that go back to the 90s for the dynamics of spin glasses. So let me say something very important. If you look at the dynamics of spin glasses, as I said, which would be a part of this, at low temperature, when you really feel the complexity, the natural timescales are exponentially long. And the type of thing that you want to study, and that I've studied for a long time, are so now what physicists call activated dynamics in this very long timescales is, for instance, aging or things of that nature. How do you move from one trap to the next and establish? I mean, it's a long story, which is totally irrelevant for statistics. If your algorithm takes a time e to the n and n is 10 to the 6th, nobody wants to try this. So the interest in statistics or in machine learning is for short time, things are working in short times, not exponential in n, right? Which is exactly what Kuglian, Aukosh, and others were doing in this. They were looking at the dynamics. Parisi was looking at the dynamics of spin glasses. In fact, in the limit where n goes to infinity and then t goes to infinity, so short times. Okay? That's which of course would not allow you to reach equilibrium. Okay? But that's the initial phase, and in fact, this is why this thing is now finding some life in those problems, because over there you want short time. Okay, good. So, so let me explain what we find. Okay, what we do in this. So summary statistics. So the first question about the behavior I just described is, how can you state the limit theorem? Your dynamics are in dimension that diverges, right? The vector itself, so you have a path in a dimension that diverges, everything diverges at the same time. You have, so how do you state a theorem? You're going to say the path of this converges to something, because it's not fixed, right? So even that is not completely clear. But happily, in most problems, nobody cares about having a pathwise limit theorem for the full trajectory of your parameters. Nobody cares. What people care are typical, a few dimensional function of this, right? You don't care about the full parameter. Typically, it's over parameterized. You want to look at a few things, right? So only a few finite dimensional functions. So of course, the question arises of having autonomous evolutions for finite dimensional projection. Of course, they will never be completely autonomous. If you have a very high dimensional dynamical system, you project it into 10 dimension. Usually it's not completely autonomous, but the idea is that it could be almost autonomous, right? And we will call these good projections summary statistics. We don't call them sufficient statistics because, of course, as you know, in statistics, sufficient statistics already exist. It means something else. So summary means that, okay, and you could have many different types of summary statistics, projections that are kind of autonomous and informative. So this could include, for instance, the value of the loss, the correlation between the classifier and the ground truth, the amplitude of certain weights, whatever you want to follow. All right. So of course, we introduce a formal definition of this. You'll see this is a little bizarre the first time you see it. And then we prove that under mild regularity assumption, the evolution of these summary statistics converge as all these dimensions grow to the solution of a system of possibly stochastic differential equation, which we call effective dynamics. This will be in a finite dimension. This will be in dimension 18, even if your thing is in the dimension 10 to the 9. Okay? These effective will depend dramatically on where you start, warm versus cold. That is, if your initialization is already informed. For instance, to come back to this spin glass thing, or this, depending whether you start, if you start at a random point, you will start at x1 equals 0 in the example I was giving, or you could start at x1 positive. This makes a big difference. One is cold and the other is warm. Of course, depending on the parameter region in which you're looking at the scaling limit. And of course, the scaling of the step size with the dimension. The role of the step size will be crucial. That's what we'll see. Okay. So what we see that the results that we have show that there are typically two phases of training: ballistic phases where the summary statistics change macroscopically in value, and some diffusive phases where they fluctuate microscopically. And during training, the evolution can start with.
So what happens is there's a time scale at which things change rapidly. Your output changes rapidly. Is that what you're saying?
Ballistic means the summary statistics move fast.
Yeah.
For instance, let's take this simple example: a random polynomial at x1 to the k.
Yeah.
One summary statistics you want to look at is x1, right? The projection in this direction.
Yeah.
If you start with a point at random, you will start at the equator near x1 equals 0, and will not be ballistic. It will essentially not move. If you start at x1 equals epsilon positive in the proper normalization, then it will move ballistically to the North Pole, right? So you may have a diffusive phase.
And all depending upon your initial data.
Initial data, size of your step size, many other things. So, and in fact, you can alternate between these different phases. Things are complicated. Okay, and in the ballistic phase, the effective dynamics are given by an ODE. And essentially, in most cases, this ODE you could see as a projection of the gradient flow of the population loss. If the learning rate is small enough in the dimension. So we will see there is a whole interval of learning rates in which the finite dimensional intuition is correct. You see an ODE that comes from this thing, okay? But then there are surprises, which are of course important. When the learning rate is at a sort of critical scale, top of a window, so you have critical learning rates, which are a whole interval where you get this kind of classical picture. Then you have a critical scaling, and above that, your thing does not converge at all. But at the critical scaling, you will see, which is usually.
So this is the step size, right? The learning rate.
Learning rate is the delta.
Is your delta and your step size.
It's not the step size, it's by what you multiply the gradient.
Okay, yeah, okay.
Okay, it's the step size as you want, but it's, all right. So you have an additional correction term, a new thing in this limiting ODE, which means that the picture, the finite dimensional picture is no longer true. And in this critical regime, the phase portrait really deviates from the population of the gradient flow. Something else is happening.
So when the delta gets big, it
gets critical. If you're above that, it doesn't converge at all. It's completely, what you get is, you don't have a limit here. Okay, so there's a critical value,
doesn't go anywhere,
which the people in machine learning call the edge of stability. When you are at the edge, this is what we call critical dynamics.
Okay.
When you are at the edge of stability, new things happen, which are very different and interesting. And this explains why, as you know, when you take people in the field, why do they do SGD? First, because as I said, if you do online SGD, it's simpler. But in fact, they all tell you that it works better than GD, right? And this is because of this correction at the edge of stability. Okay, so now you can do, there's something else you can do. You look at your system, and so you look at some summary statistics, and then they get stuck, for instance. Then you can zoom. You change your scalings of things, and you can have rescaled effective dynamics in the fixed points or the fixed manifold of this ODE. And then you will get diffusive limits. And you can, in fact, rescale these effective properly, and so they become diffusive, and they are typically given by SDs, but which are typically very degenerate. But still allow you to understand how you escape those critical regions which are slow.
So how do you get, I mean, you have to adapt your dynamics? I don't quite understand.
So what, you know, in certain regions near the critical things,
yeah,
you can zoom differently. I will explain that more. You can change the way you build your projection, okay? And then you see that in the first approximation, it didn't move, but now in this new thing, you add terms which are stochastic that allow you to get out.
So you're saying if I get stuck, I have to try again or something like that? I have to reset my.
I just, if I get stuck, no, the dynamic, I just look, the dynamics is the dynamics, you don't,
okay.
But you rescale it differently, you project it differently, and then you see something moving. Okay, well, I will give you an example. Okay, so let me give you 3 examples of this before I give you the big theorems and so on. So the first one is the one I was mentioning, matrix or tensor PCA. PCA is for principal component analysis. This is where spin glasses will come. So let's take this first simple example. Let's take spike matrix and tensor model. You may have already heard of that. So there's an abundant literature on that. Here is some of this. And so here's the model, very simple. You have this should be a tensor, I'm sorry. This is the tensor power. So you have a vector U, let's say unit vector, unknown, right? And you want to understand this vector. And you should, but here you have this vector to the power k, so it's a k tensor. All right?
Oh,
k tensor of rank 1. Yeah, this
okay,
my LaTeX is bad. Okay, so this is the k tensor power of U. Right, so it's a tensor, a k tensor of rank 1. Okay, and then what you don't have access to this, you have access to this plus Gaussian noise. So these guys are just Gaussian tensors, k tensors. Let's say IID Gaussian. Let's say variance 1, and I could put a variance here. Similarly, I could simply put a scalar here, which is a signal to noise ratio. So this lambda tells you the strength of your signal. Right? When lambda equals 0, you have no signal, pure noise. When lambda is very large, you have a lot of signal. okay? And the goal is to estimate phi nu from this noisy observations. Right? When k is 1, this is linear regression. Right? We all know that. We teach that in Statistics 101. Right? When k is 1, you have a vector, the only thing you see is this vector plus a Gaussian noise. How do you find it? You all know how to do it. Okay? So you do MLE, maximum likelihood, and then the loss is just this. The log of the likelihood when things are Gaussian is just that. Okay, and again, there should be a tensor power here. So in these models, the summary statistics are very easy. That's the inner product with U. So now think U equal E1, and this becomes X1, right? What I was given before. And this thing, which is a spherical thing, which is not very important. The important one is this one. Okay, so you have the latitude, and now, so when your step size, the learning rate scales critically with the dimension. So you have a whole regime of step size in which you have the usual convergence to the. So here, the really important variable is dimension 1. Your loss is just what I call x1 to the k. The dynamical system you get for this population loss is one-dimensional, not very difficult to understand, right? Typically, but if you start at random, you will have fixed points, and if you start randomly, so you start in the neighborhood of an uninformative fixed point, and it stays there if k is larger than 3. Right? You start at 0, the equator, right? The latitude is 0. When k equals 2, which means when you're in the case of matrices, these effective dynamics become diffusive and exhibit a transition between stable and unstable Einstein unit. Right? So when I say when you rescale, so you understand the whole thing. When k is larger than 3, to escape the fixed point, you need, in fact, the signal-to-noise ratio to diverge like this. So you need much more signal, which corresponds here to much more data. Okay? So that is understand, and you can recover. So this was understood before. This story started with this type of example where the limiting dynamical system in dimension 1. But now you will see much more interesting limiting dynamical system.
Gérard, sorry, but it seems as if you have more information when k is large. You have a larger tensor.
No.
Why do you have less information? You can just use.
Come back to what I was saying before. When you look at when you expand this MLE, much less information. When you expand this thing here, this quadratic form, right? Let's imagine that everything is fixed. If you expand this, you will have this sum of y. This is a tensor. This you will get exactly the thing I had before. This random polynomial plus lambda x1 to the k. Okay. Now,
but y is not a random polynomial. Why was this?
Y is a random tensor, right? So this is a tensor.
They are also they are not just IID Gaussians. They are
IID Gaussian tensors.
Okay, I see. So that means the product.
Yeah.
Okay.
And so now, when you look at this this thing, you get exactly the function I was giving before. And again, the problem, the true population loss is x1 to the k. When k is 3, the first derivative of that at x1 equals 0, which is the typical value on the equator, or the second derivative is 0. So you have nothing driving you away from the equator. It takes more time. And this is why you need this thing. This is a long story, but which I don't want to spend too much time here, because I want to go into more complicated stories. So here's another one. So here, this is a simple 2 layers neural net. So I'll give you now an example. The example I was just giving you here was high dimensional statistics. There was no neural net. So let's do a little bit of neural. So it's XOR classification of a Gaussian mixture. XOR means exclusive OR. All right, so to demonstrate that, we took this very simple problem and we're completely flabbergasted by the dynamical system we find. So this is probably the canonical example of a decision boundary requiring at least 2 layers in a neural network.
Yeah, I don't know what the XOR. I mean, I don't know.
I'm describing just now. So here's what it is. You have an IID sample where the yi here are Bernoulli 1/2, 0, 1. And the xi's are given by Gaussian mixtures. So let me explain what that is. When y is 1, this x is a mixture of Gaussian with mean mu or minus mu. right? So the picture is something like this. Mu here, minus mu here. And so you have red and blue individuals. When they are red, they are a mixture of two Gaussians, a Gaussian centered here and a Gaussian centered here. When they are blue, so when y is 0, the case, you have nu and minus nu. So your data is either this or that, right? We chose the simplest one. We could have put here a more complicated variance, whatever, but the simplest one to see something trivial. All right, and then, so that's your data, right? And you have a long observation of that. You have the red, the blues, of course, you don't know who is red or blue, whatever, and you observe this thing. Okay. Oops. So how do you do that? How do you classify? So you want now to learn this. So you do a two-layer.
I want to learn the distribution of these guys.
Yes. So essentially, you want to understand if you have this prior, you want to understand who is mu and who is nu, right? All right. So you use a two-layer network, right? So exactly what I described over there. So here you have a W, right? Then you have this activation function here is the sigmoid function, this one. That's what people do in practice. This W is a k by n matrix where k is larger or equal to 4. The simplest case is k is 4. You need at least 4 to solve this problem. And V are the weights. It's a k vector. So it means you have a thing like this. You have the output here is, let's say, k, size 4, let's say. Then you have something which takes linearly all this thing and gives you an output. Before that, here you have an n layer. So W here is this matrix here, the n by k, which is what I'm saying here, or k by n matrix. So what you do here, you have your activation function, sigma, and you do what I explained before. Right? This gives you your function, and G is the activation. So the sigma is here, and here you have the Relu function, x plus. That's what people really do. So we took, the simple thing for the first classification problem where you know that you need two layers. Okay, because I was tired of one layer and the simple things. So, and the loss, when you compute it, is given like that. This term is a regularization term, which in statistics simply mean you want this thing, you add a norm because you don't want your optimization to wander off to infinity, right? It's like taking a spherical constraint, okay? So when you compute this little big mess, so this is the function you want to optimize, and when you compute this big mess, it depends on 22 parameters. So the natural number statistics are 22 dimensional. In fact, you can go a little lower, it's 12, whatever. And then you can apply our theorems, which I haven't yet stated, and you see that those effective dynamics have a very rich phenomenology. They find, so you're in dimension 22, in fact, mostly in dimension 12, but okay. And then this limiting dynamics, this projection, even when n is extremely large, n could be 10 to the 9, right? So you have a large network, then this projection here has 39 fixed point regions. 39 critical regions, right? So you have a dynamical system now in finite dimension, 22, not dimension 1 like before. And this dynamical system, you wonder, does it get stuck somewhere? When I start at random, where do I start in the projection? Do I start in a good place, a bad place? Do I get stuck? How do I move to the right place? And you have here 39 fixed points of different topological dimension, of which 24 are stable. A serious mess. Of course, what you can do then is near each fixed point, do what I explained before. You can rescale your dynamics and try to understand how you escape them. Right? So I won't try giving you a picture of dimension 22, but so surprisingly, if you initialize the weights of the network randomly, right? So you have to start randomly for your parameter.
Yeah.
So you start with a Gaussian distribution, which is perfect, what everybody does. Then the algorithm will converge to a good classifier. I should have written a good classifier. It will solve the problem, this classification problem I have here. with a generalization or with the, oh, I'm sorry, to a bad classifier here. A classifier with a macroscopic generalization error, which is a bad classifier, is probability 29 out of 32, and K is 4.
No, you have to explain it. I don't understand what that.
If you start at random,
Yeah.
you have this 22-dimensional thing.
Yeah.
So you start in certain region here, you will converge to a bad classifier, right? Something that doesn't work,
It will not.
bad value of your loss function,
Okay.
with probability 29 out of 32.
So it's not a good system.
It is a very good system.
Oh, it is a good system. I'm sorry,
No, I had the same idea.
I didn't understand.
Let me explain. So it looks like a very bad system, in fact, and then it follows a degenerate diffusion. But in fact, I realized later, of course, everybody wants here probability 0 or close to 0, right? Bad classification. So before I come back to this provocative statement, let's say that. The probability of good classification is there's 3 out of 32. Right? The probability your thing works, 3 out of 32. So it's not, it seems like a lousy system. In fact, this probability is the most important characterization of the statistical procedure we've chosen here to classify the structure of the XOR network. So, okay, let's discuss that a minute. Formally, you would want this probability not being 1 is a bad thing. But in fact, if you look at how it works in the industry, this is a good thing. Because how is that done? If you Google or Facebook and if you Google or Facebook, you know how to solve XOR, but you know, if you have a harder problem, what you have a few people trying. And in fact, the only thing you need is one trained network. You don't need to train it and every time it works. You need that it has worked once. So you take 100 graduate students, 3 of them, 9 of them will find something that works, and then you keep these. That's it. You hire these. So the important thing is that this is not 0. It's a good thing. But all right. But okay, I understand the point of view.
But still, so how do you know that you got something good?
Right?
How do you know you have to write something good?
So that's okay. I should say that. Of course, like that, you don't know. Maybe you run 100 trials and 3 will work or 9 will work, but you don't know which one. But what they do in the industry is they look at what is called generalization error. It's very simple. You take your data, you cut it in half.
Yeah.
Half of it you use to do your work, and half you keep there, and then you check on this. So you check your general. If you have 9% that work, then on 9% of your trials of your trainings, they will have a small generalization error, and that's it. Okay.
But do they then still include this disclaimer? Past performance is not guarantor of future success.
So in fact, now let me explain on this model, you can understand something else. If you increase the size of this K here, which was 4, if you make it larger, the probability of success becomes this. Okay, don't read the formula. The important thing is that it converges exponentially fast to 1 when K becomes large. So this means that over-parametrization is good. Right? You need only 4 to classify successfully. But if you increase this K, all these bad events will disappear. So this dynamical system is extremely interesting, and it's a long story to study it in detail, but we've done that. And so okay, let me not explain that. The binary Gaussian mixture.
So your dynamical system is just
it's projection in dimension 22. Right? You take your. I'm saying you take this.
You follow your.
You take the stochastic gradient descent, which is in dimension a billion.
And how do you choose your delta?
This is what I'm saying. So I will explain that. So you have an interval of delta where you have a limit, and at the edge of this, the edge of stability, the critical dynamics, these are the ones that work. Okay,
Those are the good ones.
These are the good ones. Okay, so you take it as large as you can before it doesn't work at all. So let me explain what I gave you a few examples.
I thought if you took it large that you were doing, that was too crude.
That's what I'm saying. As large as you can, before it just completely goes straight. That's why it's called the edge of stability. If you take it smaller, it works, but you miss a few of the exit strategy when you are in a sticky region, right? In those critical regions.
better.
It works better at criticality, which we all like.
Yeah, that's fascinating.
Okay, so summary statistics. Let me now, okay, after all this, let me explain a bit. So remember, we're studying online SGD with step size delta. So now a little more precision about everything I explained. Possible random initialization, the dimension was D, and the amount of data is M. And so now I'm looking at given function. So now I will assume that D is D of little n, if you want, goes to infinity, P goes to infinity. And so I have functions U here, these are my projection from RP to RK. P will be very large, K is 22. Okay, and so these are my projection. And my goal is to understand the evolution of the projection of my dynamical system. Okay, when possible. So to develop a scaling limit, we need some assumptions. So I call phi of x was the average, remember, the average loss, the population loss, and I call h the difference between the loss and its average. Okay, and so I view h as a random function. In the example of tensor PCA, this would be a spin glass. This h would exactly be the Hamiltonian of the spin glass. And k, I call k the gradient, v the covariance matrix of the gradient. And here's the assumption. You can't swallow them like that, but we say that the projection, the loss, the distribution is delta localizable if you can exhaust the whole set by compact sets where you have those assumptions, bound on derivatives. Note that there are negative signs here. So when the delta are small, this bound becomes large and the assumption is easier verified. Okay? So you have assumption on the gradient, this, of that, and the second derivative here.
So the summary your assumptions.
The summary statistics should be kind of regular, nice functions of the.
Regular is not the point, is that they should be autonomous. And in some sense, this is what is hidden behind. So then.
So that slide, I went fast. So that slide was what? It's just.
This is a definition. This is a definition.
Okay.
And the theorem will be when things are localizable, we have a good limit theorem. Okay. So, all right. But you see that in this assumption, the size of delta n plays a role. So here I introduce two differential operators, A and L, which are obtained from, and now I look at the SGD initialism with learning rate delta. And I suppose that that I have this localizability assumption. And then, so I look at the linear interpolation to have a path, and I assume that the initial data, the projection of the initial data converges to something. And then the main result is that then, when you look at these summary statistics, the path converges to the path, which is the solution of this thing, right? Which is a plane SDE. In dimension 22, dimension K, right? So I have a drift H, a certain covariance sigma here, and Brownian motion in RK. So the kind of summary statistics are all this. I won't spend time there. The most interesting one is probably the last one here, but I'll maybe come back to that. So, okay, let me not go there, because that's too long. Let me just explain a little more about, okay, comparison with this classical perspective. So imagine that you have, if the operator I call A and L satisfy this, there are limit F and G, then the H, which was the drift, can be written like this. And this F here will be the population drift. If you don't, you can't read this, but F means something like what you would obtain in the classical perspective when you have the gradient of the population loss and you project it. This G is a corrector, which is something that does not exist in the classical perspective. And this is sigma will be a diffusion matrix. All right. So in a fixed dimensional, if the dimension is fixed, then of course you should just have this simple thing where f is coming from the gradient of the population loss. And this is what we find. This perspective applies in the high dimensional limit if the population corrector and the diffusion matrix are 0. This is what, of course, otherwise I would have an inconsistency. Because remember, the limit I had was minus f plus g plus a diffusion term. So this is what we find in this, what we call the subcritical regime. So there is an interval of running rates. So if for a certain learning rate, you have this classical picture, you have it for all smaller learning rates. So we have an interval of learning rates where indeed this G, the correction, and sigma are 0, and so that the effective dynamics are that you find are the same that what you would find in finite dimension. We call this the subcritical regime. Oops. And then there is a critical regime, which is just the edge of this regime, where G and sigma may be non-zero, and this high dimensionality introduces non-trivial correction for this. Okay, and yeah, so this is what I just said. So if you have something which is delta n localizable and you take something smaller, it will still be localizable. But if you take something which is strictly smaller, little o, then the G and the sigma would be 0. It's easy to see that if you have this critical dynamics, if you take a smaller, strictly smaller time scale, step size, then you will kill the corrector and the sigma. Okay. So there can be only one scaling of delta n at which you have the corrector and sigma, which are non-zero. And for all smaller scales of learning rate, the finite dimensional perspective applies. So this infinite dimensional thing will be different only at this critical thing, at this edge of stability. And so in all our example, the diffusion matrix is 0, and we call that the ballistic limit. And in this case, so we have an ODE, and this is this ODE is the one I was briefly describing in dimension 22. And okay, that's what I was saying. But then you can rescale, as I said, and then you can have diffusive limits by rescaling like this. Right? You introduce a different rescale version of the summary parameters. Let's say that this U star is a fixed point of your ballistic limit. So if you start from there, you don't move. If you rescale, you obtain diffusive limits. And okay. So this is what we do in the 3 classes of examples, and this is where we find the this interesting thing. So of course, for instance, let's come back to the case where I had this XOR with 4. You have a positive probability to start when you project on one of those slow regions, on one of those critical points. And if you start there, you don't move, right? So what you have to do then is to rescale to understand what happens in a different scale, right? And then you understand how you escape those regions. This is what we said here. All right. So when I said the probability 3 out of 32, it's if you do nothing. Now, if you have a little more data, exactly like for the tensor PCA case, then you can rescale and understand how you will escape the bad regions. Right. So it doesn't mean your algorithm may fail, succeed in 3 out of 32 cases, fail in the 29 out of 32. But if you give it more time because you have more data, then you will see how you escape those sticky regions to end up in better regions, right? So this is, but for that you need more data, right? Because you need more time for our algorithm. Okay, and this is what I'm explaining here. The rescale effective dynamics will be something like this, and the important thing here, which is different from the finite dimensional thing, is that what these diffusive limit apply to the projection, but more interestingly, we don't have uniform ellipticity. These escape are hypoelliptic usually. They are degenerate, complicated, but they still happen. As soon as you've escaped, even if it's escaping in a very specific way, then you can continue your adventure and go to the middle. Okay. Of course, I love the fact that we have degenerate diffusion because this brings me back to 40 years ago or something. This was an important topic. And of course, it was not intended. So, and I will stop here.
Is there any link possibly between this notion of summary statistics and that of relevant variables in a normalization group? And in fact, has this statistical method been applied? Can this be applied to study critical behavior in more regular statistical systems than spin glasses, three-dimensional Ising model?
You may be right. You may be right. I didn't try, but yeah, this is a very natural idea.
Of course, there is a competition with this positivity approach, which is doing marvelous job unexpectedly. So can this be used for that kind of analysis?
In fact, yeah, so coming back to the DMFT, right? The dynamics for some people have tried to use this type of techniques for renormalization thing too. But okay, I don't know, but yeah, you're right. That's a good idea. It could be possible that there are things of that nature. What is remarkable here that things are really interesting when you're at the edge of this regime. And the renormalization, I don't know if something like that happens, in fact.
Well, it's a particular interest in the critical points.
Yeah. So maybe, I don't know.
So you mentioned that you were talking to some practitioners. Just curious to know what sort of problems they're working on, the circle you're involved with.
Classification, right? That's the basic problem, which of course now is in many cases is well understood. And
so more specifically,
okay, the initial problem of classification maybe 10 years ago, or 8 years ago, because things move, was I give you a collection of, you have databases of pictures, and you want, for instance, CFAR, you have pictures of numbers. That's how you test the quality of things. And also a little distorted picture of numbers from 0 to 9, and you want to classify in 10 classes. Right. So here it was a classification problem, but you have, so that's a typical thing and then of course you have more interesting classification tasks. Classifying numbers it's a kind of an academic task, but you have a whole collection of numbers of pictures and you want to classify pictures that contain cats, right? Or contain people with this and that characteristic, right? So typically, of course, what I'm talking about here is supervised learning, which is now kind of passé, which means you had a bunch of humans saying, yes, this picture contains, the truth. Yes, this picture contains a cat, or no, this picture does not contain a cat, right? That's supervised because that's what you need to do this. Now they do more complicated things, but typically the question of there's a meta question behind this, which is how do you choose the network? How do you choose the L, right? You have a task. What you have for sure is your data, the amount of data, your data, and you have a task, classify. But then you're entirely free to choose whichever network, whatever number of layers, or whatever number of width of the layers, whichever activation, whichever loss, all that belongs to the architecture. And this is just a matter of, the ultimate goal of all this is to solve the meta question, understand what is the good architecture for something. So you have plenty of recent activity in limit theorems telling you things, for instance, when you have what is called the neural tangent kernel, which means you have limits where you assume that the width is enormous, right? But it's not what people really use, right? And in fact, you wouldn't see the picture I have here. In this type of limit, for instance, you see that the motion in parameter space is very small, right? You start from something at random and you don't move much to find something. Whereas in this picture I'm describing, this projection goes all sorts of complicated story. So, and it seems to be more what is really happening. So, you know, the neurotangent kernel is very useful, and it's something we can study as mathematicians. Here we're trying to go to this thing where we don't have a limit of infinite width, and that's why I wanted to have 2 layers. Because 1 layer is what we do or what physicists do typically. But studying 2 or 3 layers or 4 layers is really much more complicated for reason. But and typically in serious networks you would have 15 layers, right? That's at this point we don't. I can't imagine the dynamical system behind this.
Any more questions?
Well, I have a general question. I mean, so there are 2 things that you said that. So in this XOR model you were telling us about, you said there were lots of stable critical points, right? So that means the Hessian there is so you don't have any directions you can sort of locally explore to go away from it. I mean, if you had an unstable one, you could say, well, I just go in that direction.
Yeah, that's exactly.
And so now, but now you don't have any. You don't have that.
That's why you have to change. That's why you have to rescale. Your dynamical system per se, you don't have to go to this XOR. Take the simple example I was giving, the spin glass plus x1 to the k.
Yeah.
Right. When you project in the direction 1,
yeah,
right, you just have x1 to the k because the other and this thing here will have a gradient in you. And if you start with a point at random, x1 will be 0 or 1 over root n or whatever, very small. So typically, if you start there and your force is the gradient of x1, you have no force, you don't move. That's what you're saying. So if you start exactly at 0, you don't move. In fact, when you start at a point at random, you start at 1 over root n. So you do move, but it's very slow. But that's exactly what explains why you need this power, that much more data, this power p minus 2 over 2, right? So that's exactly the point. So if you rezoom around this is where you see it is limiting. It's rescale dynamics where you have on top of this thing, you have a corrector and possibly a diffusion term. And this corrector and diffusion term allow you to move.
How does this relate to the role of this critical delta? I didn't quite understand.
Okay, so if you have a delta for which you can apply this thing, right, which are localizable, whatever. What I said is that if you take any delta which is little of this delta, the assumptions still work, but the equation that you find for a smaller delta, you kill what I call the corrector and the diffusion term. You just get the plain vanilla thing, the thing that you would guess from the projection of the gradient flow of the loss function, right? So if you have anything that works, anything strictly below it will work, but give you something trivial. So the only possibility to get something non-trivial is to be at the edge of this. And to have nothing above it that would work. Because if something above it worked, this would be trivial, right? So that's exactly the same. There is only one critical regime where you see these extra terms that are helpful, okay, that allow you to move.
And they allow you to move away from these.
Yes, not always, but in the examples I had, yes.
Can one imagine that you can take delta to be critical plus little o of critical and see additional correction terms?
Yes, yes.
So maybe there's a third order correction there.
Yes, no, you're right. I was not pervert enough to think like this, but but you may be right. You may be right, definitely.
Thank you again.